Speed round. K closest points to origin is a Phong staple because it quietly tests your grasp of heaps, quick select, and distance math without square roots. Tons of candidates sort everything in O(n) log n, and leave performance on the table. We'll solve it cleanly. With a heap you can code fast and a quick select outline you can mention for extra credit. Input: an array of points, x, y, and an integer k. We must return any k points closest to 0, 0 by Euclidean distance. Important: the actual distance sqrt x squared plus y squared is monotonic with the squared distance, so we compare xx plus yy to avoid sqrt. Three main approaches. Full sort by squared distance O(n) log n, easy but not optimal. Heap, min heap, push all O(n) log n. Or better, max heap of size k keeping only the k best O(n) log k, and tiny memory. Quick select, /partition, to find the kth boundary and average O(n), then slice first k. We'll implement the max heap size k for speed and consistency. I'll also show a compact quick select. Plan with heap k. Define dist2p equals p0, p0, plus p1, p1. Maintain a max heap of minus dist2, point, or store, dist2, point, and invert logic. In Python we simulate max heap by pushing dist2, I, or dist2, x, y. For each point, push into heap. If heap size exceeds k, pop the farthest, the one with the most negative key because we stored negatives. Return the k points from the heap. Time complexity for this approach is O(n) log n, since sorting all the points dominates the runtime. We use a simple method called sort by distance. The idea is straightforward. Compute each point's distance from the origin at 0, 0, sort all points based on how close they are, and then take the first k points from the sorted list. There's no need for complicated data structures, just sorting and slicing. In the Python or Java implementation, we sort the list of points not by their x or y coordinates, but by their distance from the origin. Distance is calculated using x squared plus y squared. We skip the square root because it doesn't change which points are closer. Imagine lining up all points from closest to farthest. After sorting, we simply return the first k points from the list. Since the closest points are now at the front, this gives us exactly the k nearest neighbors. Simple slice, simple result. And that's how this algorithm works. It first sorts all points by their distance from the origin, then takes the first k entries. Efficient, simple, and elegant. The distance formula uses x squared plus y squared, avoiding unnecessary square roots. Sorting provides a clean and direct approach, giving a time complexity of O(n) log n. Now that we've implemented our solution to find the k closest points to the origin, let's check it with a real input. This helps us understand how the algorithm sorts the points by distance and selects the closest ones. We'll walk through the input, see how distances are compared, and verify that the output matches the expected result. Let's test the function using this input. The points represent coordinates on a 2D plane, and k equals 1, meaning we want the single closest point to the origin. Here's why the solution works. The algorithm calculates the squared distance of each point from the origin using x times x plus y times y. Then it sorts all points based on these distances. Finally, it returns the first k points from the sorted list. For this example, the point 1, 3 has a squared distance of 10. The point 2, 2 has a squared distance of 8. Since 8 is smaller than 10, the point 2, 2 is closer, and that is the one returned. And that is exactly what the program outputs, 2, 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the k closest points to the origin. It correctly computes distances, sorts them, and returns the expected result. It works efficiently for this test case and scales well for larger inputs. Time complexity for this approach is O(n) log k. We push up to n points into a heap that never grows beyond k items, and each push or pop costs log k. We use a max heap of size k to solve this problem. The idea is simple. The heap always keeps the farthest point at the top. We add points one by one, and if the heap grows beyond k, we remove the farthest point. This way, the heap always contains the k closest points at all times. At the end, the heap holds the answer. This is more efficient than sorting for large inputs because the heap never holds more than k items. In our Java implementation, we first create a max heap. The heap compares 2 points by their distance from the origin, but reversed, so the farthest point stays on top. Think of it like always keeping the biggest number at the front. We loop through every point in the list, considering each point for the top k closest. We add the current point into the heap, like dropping it into a container that automatically arranges itself. If the heap grows bigger than k, we remove the farthest point, keeping only the best k candidates. Once all points are processed, we prepare a 2D array to store the final answer, exactly k points. We set an index to track where to place each point. Then, we empty the heap, popping each point and storing it in the result array. Each pop gives one of the remaining closest points. Finally, we return the array containing the k closest points to the origin. And that's how this algorithm works. It builds a max heap to store only the top k best candidates, removing unnecessary far points as it goes. By the end, the heap holds exactly the k closest points. Efficient, simple, and elegant. The heap never grows beyond k elements. The max heap keeps the farthest point at the top, making removal easy. This approach is more efficient than sorting when k is much smaller than n, giving an overall time complexity of O(n) log k. Before checking the output, let's understand the problem. We are given points equals 3, 3, 5, -1, 2, 4. A list of 2D points k equals 2, the number of points closest to the origin we need to find. The goal is to return the k points closest to 0, 0 based on Euclidean distance. Let's test our function with this input. Each point represents coordinates in 2D space, and we want the 2 points nearest to the origin. Here is why the solution works. Compute squared distances for each point from the origin. 3, 3, 3 squared plus 3 squared equals 18, 5. -1 5 squared plus -1 squared equals 26 2, 4 minus 2 squared plus 4 squared equals 20. Use a max heap of size k to keep the closest points, push points with negative distances to simulate a max heap. If a new point is closer than the farthest in the heap, replace it step by step with this input. Add 3, 3 heap equals 18, 3, 3 add 5, -1 heap equals 26, 5, -1 and 18, 3, 3 add 2, 4 distance equals 20, which is less than 26. Replace 5, -1 heap now contains 3, 3 and 2, 4, the two closest points, and that is what the program outputs, 2, 4, 3, 3. The order may differ, but the points themselves are correct. This confirms the code works correctly for this test case. Our implementation is correct. It successfully finds the k closest points to the origin. It correctly calculates distances from the origin. It efficiently keeps the k closest points using a max heap. It works for any list of points in 2D space. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.